Well, in the last video, we learned about the Lebesgue measure, and we saw that the Lebesgue measure is defined on the Borel-Sigma algebra. Of course, it can be defined over something else also, but typically defined over the Borel-Sigma algebra, takes the values in the extended non-negative reals, and it coincides with our usual notion of length for intervals. And since it's a measure, it is countably additive, etc. Now you understand, when Lebesgue originally obtained his measure, his aim was not to develop measure theory. He was trying to solve some practical problem for which he needed measure. Now the way we have defined it is a very abstract way. We started with this concrete thing, and then we extended, and each of those extension theorems were just existence theorems. So we did not have any way of constructing the measure. If I give you some set and ask you, now compute Lebesgue measure for that is difficult. And secondly, when Lebesgue started out, naturally he did not just take Borel-Sigma algebra and started to define on that, because as I said, when Lebesgue was approaching the problem, he was more approaching it from the viewpoint of the supply. But Borel-Sigma algebra comes from the demand-based approach. So even to define this, you have to know what to demand. So we said that we must be closed under countable union, countable intersection. But when you are faced with the problem that here is a particular thing and I want to find its area, you will not even think along the line of countable union, countable intersection, all those things. So if you already know that there is something like measure theory in front of you, then you will make all these demands. But when Lebesgue started out, he did not have that idea. So let us see how Lebesgue originally started out, and that will give rise to something which is less complicated but at the same time less ambitious, which is called Lebesgue outer measure. Well, the original problem that Lebesgue was trying to solve was not to develop measure theory. Measure theory was not in his mind. It didn't exist at that time. His aim was to understand Riemann integration. So I give you this interval, say closed and bounded interval AB, and a function which is bounded, upper bound, lower bound, and you want to know when is it Riemann integral. Now we know that you can make these slices, that's how Riemann integration is done. And then you make the partitions finer, you take limit, sup and inf, etc. I hope you have basic idea of Riemann integration and check that certain limits exist, certain limits are equal to certain other limits, then you call it Riemann integral. Now the question is, when does a function fail to be Riemann integrable? Can we come up with a quick way of checking that it is Riemann integrable or not? Now one thing was known, that if you take a continuous function, then it has to be Riemann integral. That is quite easy to prove. The second thing was, suppose it fails to be continuous at exactly one point, like this, then also it is Riemann integrable, and the proof went like this, that of course it is Riemann integrable here, it is Riemann integrable here, but the problem is you will have one little rectangle which will contain this break. Now the point is, you can make this smaller and smaller, so you can make this particular rectangle a very sliver, and you can say that for everything else our usual idea of making a partition and approximate it using these slices will work perfectly. This thing is the only place where you may not have that result. But as I can make it arbitrarily small, suppose this is epsilon, and this rectangle can never have area more than this epsilon times the difference between these two bounds. The maximum height is this, so this particular rectangle will have area less than, if I call this A and this B minus A times epsilon. Remember, B and A are fixed given numbers. So if you make epsilon small enough, then this can be made to go to 0 as epsilon goes to 0. So you can say this little sliver of a rectangle is not going to make any difference at all. That was something that is already known from Riemann's own work. Now the same idea works even if you have got two different points of discontinuity. You will put another sliver here. Same thing works for any finite number of discontinuities. The same thing also works for any countable number of discontinuities. This much was known. Now, what happens if there are uncountable number of discontinuities? In this case, the answer is sometimes yes and sometimes no. So that's where Lebesgue started to think about. So can we come up with some kind of a characterization that for these things it will be Riemann integrable, for those it will not be Riemann integrable, and from the lead already provided by Riemann, he knew that he has to work with the set of discontinuity points of the function. His natural aim was this, that suppose I have some discontinuities here. He was following Riemann's idea that you put them inside little rectangles, so little intervals, such that the total length of the intervals is very small, because on each one of them he plans to put a sliver. So each one he will cover in a little sliver of a rectangle. All of them go from A to B. So he would like to say that B minus A, that is the common upper bound of the height, time epsilon 1, epsilon 2, etc., epsilon n, and he will say that this thing goes to 0. The problem now is that if it is countable, then he can write this sum, but if it is an uncountable set, what to do for this? What to do for total length of all the things that go to 0? And that is what first set him thinking about trying to define area for an arbitrary set. Remember, he did not have in mind sigma algebra, Lebesgue measure, or any of those things. And from this idea, he came to the idea of Lebesgue outer measure, something that we are going to discuss in the next video.